Hello, mic check. Hello, mic check. Mic check. Hello, mic check.
Hello. Yeah,
Perfect.
it's audible, right?
Yeah.
Perfect. Good. So I'll just switch it off right now.
Okay, so I want to welcome all of you for this edition of the Wednesday Colloquium, and it's an absolute pleasure to have Dr. Sudip Chakraborty from HRI to come over and give this colloquium. So before Sudip actually proceeds for the colloquium, just for the sake of completeness, the Wednesday Colloquium has a long tradition history. It was started by our founding director, Professor Homi Bhabha. And the tradition was that Bhava would come to come to the institute on Wednesdays and meet with the faculty, and then conclude the meeting with a colloquium from one of the experts who was visiting TIFR that day or within TIFR. So this has been very nicely followed because it has been a training ground for many people to think about new ideas, to collaborate with the speaker or collaborate within thinking about the ideas. So students and faculty members have been always been used to be very eager to wait for this colloquium. Now, since there are many more talks, there's been a little bit of a less enthusiasm, but still. So with that, I would like to introduce today's speaker. So Dr. Sudip Chakraborty is actually leading the materials theory for energy scavenging lab in HRI. And of course, HRI is part of our Uber family of DAE. So Sudip actually had his PhD in a very special program that BARC and University of Pune sort of started maybe almost 15, 20 years back.
Right.
And a bunch of students, actually, some of them are also in TIFR, part of this PhD program. He finished his PhD in 4.5 years, as far as I know. He's a very good student. And then he moved to his first postdoc in Max Planck. And this was in Dusseldorf, where he spent almost 2 years from 2011 to 2013 there. After his stint at the Max Planck Dusseldorf, he moved to Uppsala in Sweden, where he had a longer term as a postdoctoral fellow and then as a sort of a senior researcher who would also lead up to guide students, PhD students. So Sudip was already mentoring students at that time in his 5 year stay in Uppsala, close to 6 years stay at Uppsala. Before he took up a short assistant professorship job at IIT Indore, and then moved his entire group to HRI. But there is a long story for that, maybe some other day, how he did that move. He pulled that move in 2 years from after joining an institute. But Sudip has been doing some fantastic stuff in condensed matter physics and material science theory. We have been lucky to actually work with him in some of the problems. And his work has sort of generated a lot of interests. And he is in the editorial board of many important journals, including, which I consider important, as the Journal of Physical Chemistry, although he has a training in physics, but the fact that he is part of that. So, Sudip, I welcome you here for the colloquium, and as you're going to talk about computational advancement towards efficient energy materials.
Right.
Connecting a few dots.
That's great. Thanks, Jyotishman, for the gracious invitation. And it was really lovely having lunch with all of you. It was kind of a bit of for me a transition barrier when I see so many faculties over there in the lunch time. So I said, Jyotishman, I need some really good time to kind of prepare again my slides so that I won't kind of give you any chance to sneak out or the back door there. I saw there is 2 doors here. Yeah, so thanks for that. As you have already mentioned, so I'm from Harishchandra Sen Institute, which is kind of more like a string theory, high energy theory kind of institute, but we are having a good thrust recently in the condensed matter physics and also in the kind of interdisciplinary way of doing research there. We are doing some collaboration already with Vivek there, with Jyotishman here. And I think from morning onwards, I have a really good discussion with some of you. I think I could actually envisage some really good collaboration in the future also. Yeah, so my name of the lab is Materials Theory for Energy Scavenging. It's basically short form of MATES lab, as I always believe in lab mates, unless you cannot do something altogether. And so I'll just kind of give a nutshell and the overview of what we do. So it's basically in a twofold way. So it's kind of, this is a colloquium. I won't go to the kind of the nitty gritty of the equations and all, but I'll just try to give an overview, and then I'll kind of try to explain one physics problem and one chemistry problem and how they're all correlated together for the energy perspective. So one of the thing of what we do is the development of electronic structure code related to our own research of energy material. And in that, main two things that we are actually trying to work for a long time is it not okay? Just a moment. Should be right. Oh. Okay, it's a bit faint. Anyway. Yeah, so one of the development that we do is basically the transition pathway prediction, where I mean the conventional way of transition pathway prediction, where people are having the initial and the final point, and then do the energy elastic band. But here, what we are trying to do, we are trying to kind of marrying the electronic structure with the energy landscape to kind of get a better way of understanding of the transition pathway, where you just need only initial point, and then you can just kind of scan through over the energy landscape. The second thing which we are kind of trying to work for a long time, but it's always difficult to have like student dedicated for it code development or development of some codes, because it's kind of it's not kind of a it doesn't fetch you much of papers. So it's always kind of hard to motivate students to do something which is really equally worth of doing, like as also the application side. So that is the solid liquid interface. What we are trying to do is that, I mean, most of the electronic structure code is basically the gas phase calculation that one would do. But there you have the Poisson equation, which is the del squared phi equals to minus 4 pi rho. But then once you have the epsilon in the picture, you have a liquid of the dielectric constant, things get changed. And then you have the nonlinear Poisson-Rosban solver there. So I promised I won't be too technical in the beginning. So I just wanted to show like what these are the main two things that was kind of, I mean, starting there. The other application, I mean, based on these two development, are basically threefold. One is the ion migration, which we actually kind of extensively work on, which has a kind of implication not only in the battery, but also in the catalysis and also in the hybrid perovskite material that we also work quite extensively. The second thing is the solar cell, which mainly based on the hybrid perovskite, we are trying to understand the excited state property. And that's what something where we're trying to work much more deeper in a way. The third thing is basically the solid liquid interface, but the catalytic reaction and the catalytic reaction mechanism, where we try to see how the hydrogen revolution, oxygen revolution, CO2 reduction, those kind of things are happening. So my colleague Tishita worked more extensively on the catalytic side. So I won't go to the details into that. Okay, so just to start with a bit of motivation of, I mean, why we need energy, I think we all know. And I think this picture might make Deepa happy about the solar battery, where we have it something where you can have a solar panel, which you can also use it as a battery for the charging of a battery, I mean, for your mobile. So, I mean, we all know, I mean, there is no kind of, I mean, I don't have to emphasize it more than that, that there is kind of always a demand of energy, and to do energy material research is always worth to do that. I mean, I'm not gonna go to the statistics of that, but I think you can see the last column, and also here the I mean the renewable energy research, how much it's important. I think Vivek also work on that. I think you all are trying to do something on that. What we are trying to see from the fundamental physics point of view with a computational aspect, to see which we can, I mean, what we can do in terms of the materials prediction, and if we can actually explain the theoretical understanding of why something is happening there. So the problem is something like a needle in a haystack, I would say. So where you have a plethora of material, you have more than 105 elements in the periodic table. So one can synthesize like a millions of different materials. But then the problem is that if you have to ask that which particular material you are going to use it for a particular application, then sometimes you get really clueless. So we don't know what to do for that. So like in that case, I mean, this needle is the particular problem or the particular kind of the application or the property that you are going to use it from the haystack, which you can compare or as a kind of a plethora of material. So then what we have to do, we cannot really do this. It's kind of a brute force thing due to the funding, due to the space crunch, due to many other aspects. We cannot have like thousands of students to always dig and get the needle out of the haystack. What we can do, we can be a bit more smarter to try to kind of envisage different properties of the material. Like for this, in this case, we are trying to get the needle with the magnetic property. Okay, so I mean, that's how we sell our materials modeling research in a community. So I mean, if you don't know, or I mean, if you have the materials modeling, we can actually have, I mean, rather than doing like thousands of material synthesizing, if you just try to find the properties, actual property, what you're gonna take out, and you can do amazing job. So I would say materials modeling in demand and also the energy in demand as well. So this was what our kind of starting point. So most of our things, I was trained in physics, but my first postdoc was in chemistry, like electrochemistry, and then also in my second postdoc, I have a high pressure physics. So I have kind of a mixture of all of them. So I just thought, okay, it's a good thing. We can just try to see what are the challenging most problem that one can try to see. And I think I try to connect them all with a single string, that the energy. So that's the only string you could find in my talk for the string theorist, because I'm from HRI, so I have to use the word string sometimes. Okay, so a bit of historical evolution. So this is kind of the regime that we are trying to work is the density functional theory, which kind of started. I mean, you all know the classical Newtonian mechanics and the quantum mechanics, where you kind of have the Schrodinger equation, the single Schrodinger equation. Then you have the inverted Schrodinger equation. You cannot really solve it by, I mean, pen and paper. So we have to do some numericals on top of that. And then you have the whole history of Thomas Fermi, Hartree-Fock, Hohenbach, Kohn, and Kohn-Sham. And then, I mean, what they actually proposed in 1965 is basically the density functional theory. So the main essence of it, rather than going to the nitty-gritty of the actual derivation and all, is that you are actually considering the electron density rather than having solved like thousands or millions of Schrodinger equation there. And so that kinds of makes your life a lot more easier, and that's what we are trying to do. And so this is the DFT, that is our main formalism or the main kind of workforce that we try to do. A bit of trivia here is that, I mean, Walter Kohn was a theoretical physicist who actually got the Nobel in chemistry. So I think that's also another defense of our self, being a physics trained, doing something which is kind of relatable to the chemistry and also the interdisciplinary science. Yeah, so I think he's the best example for us and a role model in a way. Okay, so in case if you need to know more on that and anything kind of more technicalities, you can always mail me. We are always kind of reachable. And HRA has a really good visiting program where we always love to host as much as student as possible. So like our last VSP program, we actually got 1,300 application. We could just have 13 out of that, which is a bit of Monte Carlo. But nevertheless, I mean, you can have it. So we have that kind of the infrastructure at least to host student. So any of you in your kind of in your starting of PhD, or even in the kind of on the verge of your PhD, if you would like to learn something why it's happening, or if you would like to do something in the DFT or also the beyond DFT, I think Omartu is here. I think Vamshi is here. Then I think Bahadur is there. But even in that, if you want to know something on that, you please let me know. I would love to kind of host you in HRI and where you can actually learn. So I have a good computing time there, which we are really lucky to have that. So I think we can actually really tackle like a high level problem with really bigger system. Okay, so by saying that, so this is one of the kind of the development that we do. I mean, I'll just try to show a bit of that if I'll actually kind of go the actual problem. So one of the development that we did with Professor David Wells was the transition pathway prediction. This code we developed almost 10 years back, which is actually in this repository. You can always go, it's free code. You don't have to buy anything. Why it's important, I'll just show it in the next slide. And we developed the code, and not only we developed, we kind of tried to put some experimental validation and also the vice versa of what Claire found in her experimental NMR study, where she could actually find the lithium and amine migration in the LiMNO2. Anyway, so basically the idea of the code is like you have, like I was telling, you have the initial point and the final point of your transition pathway. And this is how we do the nudge elastic band to actually predict the transition pathway prediction. We do it regularly, but then there are a few problems with that. The problems are like you need to know the starting and end points. So let's say if you don't know the end points, then you're kind of a bit clueless. Or if you get an end point, then you are clueless also to know whether you are actually getting the correct one or not. So there's always a statistical ensemble that one can actually have it with the transition pathway prediction. So one can have like more than one transition path, and then you can kind of sample them all together to get kind of a this particular, I mean, energy landscape plus electronic structure into that. There's also like a multiple atoms and the large system requirements. So once one kind of, I mean, then we try to kind of couple it with Professor David Wells' code, which is single-ended hybrid eigenvector following approach, which actually does this. So you start with the initial point, and then you kind of see the whole energy landscape to actually find the transition pathway. Our job was to kind of make them married together so that we can have the electronic and the ionic diffusion with much more accuracy. We could actually already proved it correct. I'll just show you in a way that there is a kind of experimental system of LiMNO2 where we could actually do that. So the reason we could do that is because, I mean, you have the potential energy surface where you have the first derivative and the second derivative of the total energy. The second derivative is basically the Hessian matrix, which is really kind of a bizarre to handle. What we do is that we just take the first derivative, and then we try to put it in the Rayleigh-Strith ratio, do like a LBFCS scheme of minimization, and to get the energy minimum. So basically how it works is like, let's say you start here, which is your initial point, and then you kind of do a already angle search of all the different local minima there. I mean, all the possibility, do a DFT calculation in each of the point, and then you go to the next step. And this go to the next step is totally up on you, like how much you want to go. And then you just go like up like that, and then you go down once you hit the lambda, which is sign changed. And this you can do for not only one particular case, but a lot many cases. And then you kind of sample through all of them together to get the transition pathway. And the reason we could get better results is that I think we have, I mean, we have it on the fly. So you could actually use, I mean, you could actually save a lot of time in the computation to do the transition pathway finding there. So, and I am not showing the actual the system. I mean, because I want to talk a bit different than that. The other development that we're trying to do is trying to kind of manipulate this VEE, which is the electrostatic potential that one would like to see. So basically, in your solid or in your gas phase calculation, though we claim a lot from our DFT calculation or the electronic structure calculation, at the end they're all kind of a gas phase calculation. So we have to be really honest with that. And then the thing is that, but in order to kind of put up the liquid, the solid liquid interface or the liquid medium in the system, you cannot really live with this particular VE, which is the Poisson equation. It kind of transforms to del epsilon del psi equals to minus 4 pi rho, which is the nonlinear Poisson-Boltzmann solver. So what we're trying to do right now is kind of develop our own standalone solver, which can actually have, so if you just give me any electronic structure code calculation of the results, and I can just plug it our the solver, the nonlinear Poisson-Boltzmann solver, to give me the electrostatic potential under the presence of the dielectric constant there in the epsilon there. So that's what we are trying to do. So with this main two development that we do, we have this different. Please feel free to ask me any question if I'm too fast or, I mean, otherwise I'll feel like maybe either you're understanding all of them or maybe I'm doing something wrong. So feel free to ask. Okay. So there are like three different possibilities of kind of application that one could actually see. One is in the catalytic pathway reaction. One is where we are trying to see the ion migration in the battery. And then the last one where we are trying to see the perovskite, the hybrid perovskite, the electronic property and the optical properties. So I'm just, as I said, like I'm just going to talk one chemistry problem and one physics problem, but they're all connected with one particular issue, which is the Rashba splitting. So that's we are going to talk in the next few minutes. Okay. So first I'll start with the hybrid perovskite. So this is a perovskite. It started, I mean, we all know the silicon solar cell, but hybrid perovskite come in the picture in 2009 by Professor Miyasaka, where he started to make it like there is an organic cation part, there is an organic part of the system. Then there is also inorganic part, which is like your even PBI6 or whatever the inorganic that you could see, which actually likes this. So this is inorganic perovskite, and this is your hybrid perovskite. So you have extra organic cation there. And apparently, you can really synthesize it quite well. It's quite cheaper. And right now, the efficiency of the hybrid perovskite is almost comparable to the silicon solar cell, which is around. So, and every year they have a record, like world record of efficiency. But honestly, they don't have any idea why they are getting that of world record of efficiency. And there we are trying to play a role there from our electronic point of view, electronic structure point of view. Okay, why they're getting that much of efficiency or stability. Because they're all related with the fundamental aspect of electronic structure and the ion migration that I'm going to talk a bit. So this is what we try to see. I mean, we try to see the hybrid perovskite. There's an interesting problem, which I also show it in the schematic here, which you can see it more bigger here, which is the Rashba splitting. So basically, what happened is that life is beautiful when you have a direct band gap, you have the valence band, conduction band all at the same K point, but then conceptually, when you have a heavy element, which is quite evident for a like a hybrid perovskite material or for any kind of heavy element like lead or bismuth, and in a non-centrosymmetric structure. So there is a structural inversion symmetry which is broken. Then what happens is that your band structure, which is kind of this valence band and the conduction band, they get splitted like this. This is schematic, but I will also show the actual band structure where you can actually see how they get splitted. So the idea is that once they get splitted here, this excited state electron, they cannot just come back to the ground state, but they kind of go or settle for a metastable state for some amount of time, and that the electron, which is kind of getting there in that excited state electron, as excited state electron, that kind of makes us tune the recombination. Okay, and you know, like, I mean, if you want to delay the recombination, you have a better efficiency in the solar cell. If you want to kind of want them to recombine faster, you can get a better LED. And it's that electron, we actually use it recently, which we believe at the first time in the world, to kind of see how it could actually enhance the efficiency of catalytic material from the HR perspective. I'll show that also in a moment in the second phase of the talk. So did you get the concept? How does it work? Yeah, Vivek. Yeah. Yeah.
Why the
So no, the gap is not the same actually, because you have the kind of the shift in terms of your K, right? So you have a EK diagram, and then you have the non-centrosymmetricity in the structure. So what happened is that the conduction band, which is like that go a bit shift. So there is a kind of a transition from your conduction band to the valence band, and as a matter of that excited state electron which was there, it doesn't, you couldn't find any state directly below it at the K space. So it kind of go to another state where it can kind of reside for a moment, and then it can come back. So basically, what you are trying to do, you are trying kind of delaying the recombination there. So, and in kind of solar cell, you don't want them to recombine. That's the whole part. But
just direct to indirect transition?
it's not only direct to indirect transition, but also like the splitting has a spin texture dependency as well. I'll show you that. So basically, what happened is that this is a EK, in like a delta E, delta K kind of a transition, but there's also the spin texture which is changing. So, I mean, if you'll see, the excited state property there, I mean, it's kind of a spin forbidden and spin allowed transitions are also there. So we're actually trying to play around that as well, because all this system also have a spin texture I mean, I'll show some of the spin texture, then you can actually understand. So yeah, I mean, essentially it's a direct to indirect transition, but there is also spin in the story. And it also comes with kind of the non-centrosymmetric structure in the system. So what happened is that, I mean, I'll show one good example of that. So this was one of the hybrid perovskite system where it has a mixed halide, mixed cation hybrid perovskite. And that time it was back in 2000, like 90s or 20s, they could find around 21% efficiency, but they have no idea why they're getting this much of efficiency in this particular material. But if you see the band structure there, mostly in this prominent splitting, you could see there is some splitting there. And it's not only the band structure, but you could also see like SX, SY, and SZ, the spin component. That is also kind of it's not, my student is not plotting it properly, but it's actually the spin component which is not showing that way. So, I mean, there is no intensity on the SY. So there is a kind of anisotropy of the spin texture. Please.
Just quick thought.
Yeah.
Yeah. So the Raspa splitting essentially splits your band.
Right.
So you have this up spin and down spin.
Right.
But what is that making indirect band gap? I mean, you have somehow shifted the midpoint of the two things.
Yeah.
It's just to show that, or
can I draw it? Probably that would be better. So, so let's say, I mean, if you have like this, I'll just show the conduction band case.
yeah.
So let's say if this is your EK diagram, right? Where so once you have the rush bar, you can just see that this thing's it's kind of going like this.
Yeah.
So you have this point, which is
And
kind of getting
the downspin will be in this
also,
way.
right?
Yeah.
And then what you get is that this is kind of going here. I mean, there is a kind of shift here. So there is a delta K and there is a delta E, which is changing
Okay,
there.
what I was thinking is that you had this band,
Hmm.
that splits, and there's a degenerate band
Right.
up and down.
Right.
That splits both ways symmetrically.
It's not actually, it's not always symmetric. We could find that some of the band structure, they're actually, I mean, in the ideal case, they should be symmetric, but yeah, right. But they're not always symmetric. So what happened is that when you calculate the alpha, which is 2 delta E by delta K, you could find the alpha in this region where you have it from gamma to some K points, let's say. And the same thing here, they are not equal actually. Yeah.
So what you're saying is that the raster splitting gives you the asymmetric.
Right.
kind of, band.
Also, because there is also spin texture play a role there. Resonance is important, right? Yeah, that's a bit more complicated, but we also are trying to settle that issue as well. Like, but right now it's the raster splitting that we're trying to play around. Is it clear? Okay, great. So, yeah, please.
So you mentioned that this happened when you have a non-centrosymmetric system.
Right.
So if I sort of decrease the symmetry of the system by doing some external, let's say, external
Decrease what?
the symmetry of the system by some
right,
external
right.
element, then am I supposed to see this delta K increasing and
Yes.
same trend observed in the lifetime?
We're trying to do that. So what we're trying to see, okay, we started with some really nice, super good looking centrosymmetric structure, and then we're trying to see some external strain, uniaxially or biaxially, so that it could kind of convert to the non-centrosymmetric structure. And then it can induce some splitting there. We're having it. For the 2D materials, it's inherent non-centrosymmetric because, I mean, that's what I'll give you an example where we try to connect the Rashba splitting with the HCl. That's the 2D materials where you could see that. Yeah.
And in terms of lifetime, how much like we expect the increase in the lifetime?
Excellent question. So that is we're trying to calculate right now. We're trying to calculate the excitonic lifetime at that particular point and try to connect with. So right now there is a system my students are doing at the moment, but we're trying to connect the excitonic lifetime and also the lifetime at that particular electron in that states and try to connect with the Rashba. So that is actually exactly what we're trying to do. We're trying to do it on a 3 to 9 system like cesium, bismuth iodide. Yeah, please, Bahadur.
So in this particular slot, at gamma point, we have now completed.
That's true. Yeah.
But the system is just breaking the inversion and not time reversal. How
Right.
can this at gamma point, how we cannot have two-fold degeneracy?
So it means one of the symmetry would be kind of broken? How?
Yeah, because
Yeah.
if you see in this Rashba system,
Right.
my spin should be two-fold degenerate at gamma.
Right.
That's why construct of time reversal.
Yeah.
But in this particular picture, I see
Yeah.
that
This is just a schematic. I mean, and also that one. I mean, the real band structure is something here.
sure, I
We
agree
can
with
take
that. But what
example,
I'm saying is like how you have offset from your some high symmetry point in the Rashba.
Okay, good question. Yeah. So basically, so you have the high symmetry point from the Brillouin zone that you can get it from there. And what you try to see is that you try to change the lattice parameter such a way that the Brillouin zone also would be changing with a different space group. And how that kind of changes your alpha, I mean, consistently. So what we can actually see if we'll just calculate the 2 delta E by delta K and changes with different parameters like the lattice parameter or the phase, I mean the space group for the knapper, you could actually see that. Yeah.
Sure. Okay.
Great. Oh, so I couldn't complete the story here. So so what we could see is that so this has a good efficiency, and that efficiency is actually coming from this particular Rashba splitting, and then we could also see the spin textures and all. And but then exactly the question that you're asking, that there's like most of the structures or most of the, I mean, crystal structure that we could find is basically the centrosymmetric structure. And so I kind of, whenever I ask my students to find some non-centrosymmetric structure, we end up having really big system, which we cannot really handle with our resources. And so what we're trying to do, if there is like a centrosymmetric structure, we try to put some uniaxial or the biaxial strain so that there will be some kind of a space group transition from the centrosymmetric to the non-centrosymmetric, where you can actually have the splitting. And there you can actually see how this is. So there is a lot of repercussion when you have the excited state electron in the Rashba splitting changing. I can show on the alpha. Yes. Okay, it's some other noise. Please.
This band structure calculation.
Right.
So why needed, cannot be calculated using this typical vast program?
Yeah, these are vast calculation.
So you said that you have to really develop a new code.
No, for this, no. So that is for the transition pathway. So no. So for the transition pathway calculation, where we would like to see the ion migration, there. So this is a typical vast calculation. But for the ion migration calculation, you need to develop a new code where, because the vast calculation, the ion migration was not kind of enough to show. So I mean the work that I was showing this the Kimmet paper with Clea Gray. Okay. Yeah, well, I'll just try to show that. Yeah, this work where you have this lithium MnO2 migration. So actually, Gerd Cedar from UC Berkeley, who moved from MIT a few years back, he proposed that the lithium and Mn are kind of migrating together in a half lithiated MnO2. What I don't want to say, but what we kind of tried to prove them wrong, and we actually proved them wrong because in the experiment, what Claire found in an experiment that they're actually going one by one, and that actually we tried to find. So this transition pathway that we could calculate is from actually that particular interface that we developed there. So yeah, that was the thing. Okay, so I was talking about the hybrid perovskite where it started. So this work was kind of it was done like 2000 19 onwards. So by Amitav, who right now is faculty. So he was my first PhD. So right now he's a faculty in IIT Jodhpur. But then we started kind of working on more inorganic perovskite material. And one of the first work we're trying to see is the cerium tantalum nitride. So there's few works which have been reported both from the high throughput selection and also from the, synthesis point of view, the CETN3, so nitride kind of material. So what actually the beauty of this material is that it has already a kind of a splitting here in the conduction band and also in the valence band. It has a good dynamical stability, which you can see from the phonon dispersion. Otherwise, if you will try to put a pressure or strain, you need to always check a phonon dispersion. Otherwise, you cannot really comment that they're synthesizable, or because they are not dynamically stable in a way. So we did that, and what we could find, we're trying to see how this. So this is exactly what I was trying to plot there, but in the conduction band. So what we're trying to see is that if we'll put up some pressure, and we're just trying till 8 GPa. Because before, after that it's kind of all dynamically unstable. We could find that the Rashba splitting is not only the Rashba splitting and the band gap is changing, the spin texture, this was I was talking about, the spin texture, that is also changing somehow. So if you see, this is the SX, SY, and SZ component, and this is your spin texture. You can see how the red, the splash of red, it's actually become a kind of a red spot here. So how the spin texture is actually changing with different pressure. We could also calculate the alpha, as I was telling, like the right hand side and the left hand side, they have actually different alpha there because it's kind of an anisotropic system. And also in the conduction band and the valence band, they're actually different. So this was kind of a theoretical prediction, and we're right now talking with experimental people who can kind of synthesize this kind of material, CTN3 kind of material. They say it's a bit hard, but I think we are on it. So we're trying to do it as much as possible. So this was one of the thing, because my idea, which kind of leads to this, is basically the piezochromism. So piezochromism is basically where you're trying to change the pressure. You're actually putting a pressure and change the optical properties, the excitation property. Because why is piezochromism? Because your color is changing. Naturally, the band gap is changing. And the idea is that rather than kind of synthesize different material, like 10 different or 20 different material, you just synthesize one material and try to kind of put a pressure within the dynamical stability range. And then you can see there is a phase transition happening there, which might be interesting for the application that you are trying to develop. So basically, this is what we are trying to see. So you have one particular material, and I think, for our experimental friend, it's not always possible to synthesize many materials to see which material will click for this particular application. But let's say you want to you have synthesized some material, but the band gap which you are hoping for, it was not clicking for this particular material, then we're trying to see how the pressure would actually change that. And that is what the piezochromism started with. So we did something like long back in like iron tetraboride kind of system, and also in the thallium, where we could actually see there is kind of a drastic phase transition. So this was done with Professor Hokang Mao, who actually kind of who actually invented the diamond anvil cell, the DSC there. It was started with a metallic system. We're trying to see if there is any superconductivity with high pressure. Just tell my student that time say, okay, no, we're not getting any superconductivity in nature, but we're getting some band gap. It's kind of like a transparent phase of those material. And you could see they're all kind of a dynamically stable. And then in 2017, I found this paper from Stanford of Karunadasa, where she could actually find the metallization of halide perovskite with a dynamical stable region. And we could find that, okay, so this is something, another way to try to tune. So what our one of the target is try to kind of facilitate the thinking process, where we can have, rather than going to many syntheses or many kind of experimental validation, if you have one thing and then we're trying to get something out of that, which could be probably usable for the application side. So this is where kind of trying to heading to, and we're trying to get different materials to try to see how it could actually happen. The second thing what I'll kind of talk about, which is also related to the Rashba, is in the chemistry problem, where I was telling this kind of, I mean, we are working on a lot of catalysis, I mean, catalytic material, and with many of you. So what we are trying to see, we try to see 2D catalytic material, we're trying to see different catalytic reaction mechanism, but what we kind of get into is that in the photocatalytic, this is the basic slide of the photocatalysis where you have the CBM and the VBM, and from the CBM position and the VBM position, you can actually say whether it will be good HCR or OER. Our target is actually, sorry, okay, I think I should just say something before I'll move on to the photocatalytic Rashba splitting. So what, I mean, so this we all know, right? I mean, you have a CBM and VBM, and then you kind of see how good a HCR and the OER, and then one can actually calculate the different pathways from the adsorption study. Like this is the oxygen evolution reaction. One can see the OH and OH. I think the chemistry could correlate it quite well. And then you can actually calculate the over potential. So this is a beautiful life concept. Life is not that beautiful. You have always a bigger over potential, which you could actually try to kind of overcome. And in the H year, you have the Volmer-Tafel-Herovsky reaction, where you would like to go to the delta G as 0, as close to as Z. But what we thought is something different. I mean, based on that, is how about connecting the Rashba splitting, the Rashba band structure splitting with the catalytic enhancement in the photocatalytic material. And we believe it could be a new way to think and to perceive this particular application. So the idea is that, I mean, once you have, so basically this is your splitting. So we try to get a guinea pig system of BICLS monolayer, which is basically intrinsically monolayer system. So there is already a non-centrosymmetric structure there. And there is bismuth, which is heavy element. So there is already a spin-orbit coupling there. So we could actually see your conduction band is getting splitted like this. And what we thought is that, I mean, if this particular, I mean, in this board also, if that excited state electron is kind of getting here, somehow below the conduction band as a metastable state, that could be help in the 2H plus 2 electron equals to H2, the hydrogen evolution reaction. So can we really get that? And interestingly, we could actually find that. What we could find is that this is your alpha, which is basically your Rashba splitting there, which I kind of 2 delta E by delta K. And your alpha is kind of getting more. That means you have the more probability of the excited state electron being in that particular state below the conduction band minima, and that increases your HCR activity by decreasing your delta G. Because delta G is nothing but this is your thermoneutral condition, and this is your hydrogen absorption energy, the hydrogen free absorption energy. So
Can I ask you a quick question?
Sure.
Sudip? So I understand the idea of the splitting, but the point here is, how do you access the proton reduction potential? Was the material not able to do the reduction? Was it not able to do the reduction, and hence you use the strain to induce it? So have you measured the redox potential of that electron?
So
does it change from a non-strained system?
It's a great question. So BICLS monolayer, it has no promise for the catalysis, I would say, to start with first. I mean, that's where so if you want to make a problem, or if you want to make something a big problem, you start with where there is no promise, and then you try to develop a promise into that. BICLS has no kind of potential to be a catalysis material. And then if you see actually the HCR activity there, the delta G is far from thermoneutral condition. So naturally your redox potential and all of this are really something which is not experimentally viable, I would say. And then we try to put a pressure, I mean, not a pressure, but here the strain. And then we see it's kind of slowly changing, and 3%, because beyond the 3%, we could actually not get the structure stable. It all distorted. So 3% is the maximum that you could see. And when you put a pressure in this particular BICLS monolayer, you could actually find that, I mean, your alpha, the Rashba splitting is increasing. And then we're trying to kind of adsorb I mean, so this is the structure. So this is a BICLS structure. You have a Rashba splitting, which is here, which is a pristine structure. We have a spin texture there also. And then we're trying to adsorb the hydrogen there. And then we're trying to put a strain there. And what we could find is that when you're putting a strain there, your alpha value, this splitting is getting more. I'll show in the some of the spin texture plot. Yeah, so that is changing with yes. Okay. So we have it estimation in terms of the delta G, and that we could actually we already have the plot for that. So this is something here, and which is going here.
Okay, that's
Yeah. Yeah. So so this is what you can you have a pristine cases, and then you have the green one here. So this is just like the simple H plus plus electron to H2, like a HR activity with a Volmer pathway. Yeah. It's a good question. The Volmer-Tafel or Volmer-Herovsky pathway, one can actually eventually see with the transition pathway prediction that we did. So what one needs to do is that, let's say you try to put H separately in a surface, and then you try to see that migration pathway. So that can be actually done. So like whether the Volmer-Herovsky or the Volmer-Tafel pathway is kind of favorable, that can be done. We haven't done it here, but in principle that can be done. Yeah. Sure.
Means that either you are sort of compressing and stretching the 1D layer.
Yes.
So at when the strain percent is 0%, I would expect that no such splitting is happening.
It's a pristine case.
Yeah, pristine case. So no such splitting is there.
There is splitting. The BICLS,
Okay.
it has a splitting. This is your, so there is a splitting you can see here.
Okay.
Okay. So if I'll show you the actual table, you can see. So this is your 0, where you have some Rashba splitting value there. Okay. And all this calculation actually done with spin orbit coupling with hybrid functional, which is a bit computationally expensive. But you need to kind of take care the actual physics for that. Because if you just do like a simple PB GGA calculation, you may not be able to find that one. But there is already a splitting existing. What we're trying to see is that, so that was the only good point about the material, that there is a splitting, but the HCR was hopeless. But then we're trying to see if you can increase the alpha, could it actually enhance your HCR? And so this opens up a kind of a new way of doing things, is that, let's say if you have a 2D material, any damn 2D material you are trying to think about, you just try to put up some heavy element on top of that. Your band structure should change differently. And that can enhance some HR activity in your system. So, like, let's say if you consider a PT, like a single atom catalysis, people try to talk a lot, single vacancy atom and all. So you just try to put up a pinch of platinum. Okay, I cannot say pinch of platinum to experimental people in that way, but so you just consider like one small amount of platinum or some heavy element that you're going to put, that actually changes your band structure.
So in case of when the strain is negative,
right.
So the splitting should increase or it should decrease?
Okay, that's not in our hands. So at this case, what we could find is that your splitting is actually kind of enhancing with the strain, but it's not the other way around in the other side of the strain. But it's kind of, I think it depends on the material, how you're going to see that.
Yeah, because what I was imagining that even if you're compressing, you're breaking the centrosymmetric more. Right. So one would expect, like, I may be wrong, I was expecting a U-shaped curve, something like that.
Yeah, so that is the thing. You cannot really get all the time consistent in non-centrosymmetric nature in your field, right? It's just a matter of what local minimum you got trapped into, right? You might trap into one local minimum where you can put some strain that can eventually kind of kick it out to a much more better global minimum there.
Okay. Thank you.
Yeah. Okay. Shall I? Okay. So this was kind of the band structure that we're trying to say, and then we see, like, with different pressure, with different strain, that we could see how the band structure is changing and how the spin texture so spin texture is here. But basically, this is some of the values where we are trying to kind of plot for your reference how the alpha values is changing and how exactly the delta G is also changing when you have a HR activity. We could also see the spin texture. I'm not going to the details into that as it's kind of a colloquial. I'll just show what are the main concept of the problem, and one can actually extend it for any different cases if possible. So then there is also kind of a spin texture, which is actually changing with like SXS or SZ, which is changing with some different pressure regime. So, okay, this is not under review. This is already published in JMCA recently. So this is what we could find, and this is what the picture in a nutshell that we could actually see. And this is our last kind of vision, what we'd like to see how, I mean, for different cases, this not only may not be kind of only for the water splitting or the HCR OER, but for any other cases, how exactly you can see, like even for the methane decomposition or ammonia decomposition for any feedstock molecule, how one can actually see, I mean, this particular delta G changing with strain or with a Rashba splitting enhancement into that. So this last thing that I would like to show is there's enough of kind of predicting properties from the structure. We are trying to do right now, if you'll give me some properties, we'll try to predict some new materials into that. And that is what we are trying hard right now. We are in a quite childish stage in that, but that is what the invertible neural network could do, like an inverse material design, and that would be really attractive for the experimental friend, where you can give me some property, or if you want to see the band gap or something. So I want this band gap, or I want this excitron polaron at some point in future. We try to get the appropriate material for that. So this is what we are trying to do right now as one of the quite ambitious project. So with that, I would like to thank all of you. I didn't mention this recent Nature materials which we could publish. So Tishita did all the calculation for that, where she is the equal contributing author, but maybe some next time she will talk on that. Thank you.
Thank you, Sudip. Questions?
I hope I was time.
Yes, you were perfectly on time. So thank you.
Yeah, I have a
Yes,
question.
you have the mic. Good.
When you see that there is a Rashba splitting and you
Yes.
said that there is a metastable state,
Right.
so does that mean that there is an additional band between the?
Yes. So it's kind of I wouldn't say it's like a proper band, but it's kind of a metastable kind of electronic state where your electron can reside into for some time. I wouldn't call it a band, because unless you can calculate the lifetime of that particular electron, like I was discussing, you cannot really say, okay, you have that particular
And
band.
why is it metastable?
Because at some point it will come back, right? I mean, that's the law of nature. I mean, it will be kind of a go into that metastable state, which is kind of below that conduction band minimum, but at some point it will come back. I mean, that is how the recombination happens.
Yeah. Hi.
Yeah.
So I'm just curious about the rate of electron transfer. So how do
Yeah.
you compute that?
We haven't done so. We are trying to do that. I mean, that is also another thing, like it's kind of related to the lifetime of the electron in that particular level. So, I mean, once you get calculated that one, so like we're trying to get the extronic lifetime right now, calculating with the GWBSC, like, body physics interpretation of the this particular lifetime of the electron in that state. Once you get that, I think getting the rate of transfer wouldn't be very difficult.
So the increase in lifetime of the excited states,
That's
does that
that's our gut feeling is, but I mean, honestly, we haven't calculated that, but I would say that is the reason that you are having the HR activity. But yeah, I mean, we are actually trying to, there's some calculations running right now for the calculating the lifetime in that particular step.
And then most of the time you are looking at the bottom of the conduction band, right?
Right.
But there will be many other bands, and you could
It's a
have a
conduction band
population.
minima, I would say. So we are just trying to look. So there is a lot many papers published, which is kind of they're showing Rashba splitting anywhere in the band structure, which is not the correct way to do. You basically see how the conduction band minima, the splitting should be at the conduction band minima and the valence band maxima at the extrema point, because that's where
But there should be some population, among different
there'll be some
bands.
population, yeah. But I mean, so we're trying to get it as a reference. Iske niche, there won't be any kind of splitting, I would say.
Okay, yeah,
Yeah.
thanks.
Yeah.
So I have one question.
Yeah.
So you mentioned that when you have the splitting, basically the conduction band minima and the
Right.
valence band maxima sort of shape. So the lifetime of the electron is increasing, but what happens to the excitation oscillator strain? So because that will also dictate how much photon you are able to absorb,
Right.
finally dictating the
right.
quantum efficiency of the overall
So,
process.
so right now in the CST-BI2I9 system, we're actually trying to calculate the excitonic lifetime. And we also got some really interesting result where we have a kind of a demarcation between the 1-year exciton and the Frenkel exciton, also in the similar kind of material, but just changing the composition there. We could actually find that there's something into that. It's there actually. Yeah. Yeah.
So you talk about that metastable state.
Yeah.
What is the nature of that state? Like how that state comes into the existence when you put the strain, then it come into the existence.
Right. So this
How-
again in the same kind of a do loop of answer I would give, like when we are trying to calculate the lifetime of the electron in that particular state, unless we can actually estimate that, it's quite possible. We are actually doing it right now, but probably in the next talk I'll show you something that actually the numbers, but that can actually give us the idea about how it looks like. Yeah.
So is there, is there any possibility, there are some system where this photo intercalation things happens.
Sorry?
Photo intercalation.
Photo intercalation.
Some ions goes into the system, they make a state in between the band gaps. So is
Yeah.
there a possibility these
But
metastable
what
state?
do you mean by photo intercalation in terms of the photo-induced intercalation?
Yes, like when you excite your system, the ions goes inside your system.
Right,
Like
right,
lithium
right.
ions
Yeah.
and the sodium ions
Yeah,
goes.
we are doing some problem. I haven't shown it with Professor Miyasaka, his group in Japan, where we're trying to see how the photo-induced ion migration is actually happening. So if you'll have a photon induced on your system, how your halide is getting migrated through. And once it will be getting migrated through, you have the intercalation process initiating there.
So I'm just thinking, can we imagine that metastable state in that respect or something? Do
You
you
can imagine that. I'm not sure if I'll be fully confident on that one, but yeah, it could be a proposition. But I mean, unless I can have the real number, I couldn't say actually about that. But yeah, I mean, one can see it's a nice proposition.
So what is the advantage of selecting this perovskite structure for this purpose?
What is the
Advantage
uh-huh?
to select this perovskite structure for this purpose? Can you select any other 2D material structure?
Yeah. So it's just a matter of fact that I have some collaboration who are working on hybrid perovskite, and then it's kind of motivated us to do something in the hybrid perovskite. And it has a good question. So there is always some good question to answer. So the hybrid perovskite material, they get many efficiency, but there's not the understanding of why they're getting the efficiency there more. And that's how we tackle it. But it could be really done. I think there is a kind of a good PRL on giant rush bus splitting in kind of a GET kind of system. So there is always the other material that one can see as well. It's just matter of fact of coincidence that we try to happen to work on that. So that is a kind of, I just try to give a conceptual way to see that these are the possibility, and one can have the possible implication and the repercussion on that thing. But this has no boundary of imagination of material in the real world. Yeah.
Because you brought in two different concepts, which is the strain-induced behavior and at the same time ion migration.
Right.
Do you find the ion migration can be suppressed on introduction of a strain?
Ion migration, okay, that's a good question. So ion migration can be suppressed if you're changing the cation size,
Agree.
because that is more prominent to kind of suppress your ion migration. With strain, we haven't tried it, but
Because one thing from a catalysis point of view
Right.
that we spend a lot of time working with is trying to understand the crystallographic orientation and the physical, direct lattice that is
Right.
exposed.
right.
And therefore bond strengths, bond lengths, and all
Yes,
those things matter.
yes.
And when you're introducing strain, I would
Yes.
assume that gets perturbed substantially.
Yes. If
And
you'll introduce strain, there will be change in your octahedral tilting. There will be change in your, the Goldstein tolerance factor. So naturally, your structural changes will be there. In that way, you can say, yes, one can get the ion migration impact. Yeah.
Okay, that's the question.
Oh, I think you have some question.
Hi.
Yeah, please.
So, is non-centrosymmetry or centrosymmetry the unique defining parameter to define this Rashba effect in?
So far, yeah. I mean, what we found is that mostly if you have a non-center symmetry structure, your inverse symmetry get broken. That means, and if you have a kind of intrinsic spin-orbit coupling there, you could see such kind of splitting. But we also have published something where it's a really good centrosymmetric structure, which is CH2BI-BR6. It was pure theoretical work where we did something on that. But you could see there is no as such pronounced Rashba splitting, but there's a pseudo Rashba where you have the spin texture dependency of band structure, which is changing there. So I would say the spin orbit coupling is more important than the actual structure. But if you really want to have more Rashba splitting, pronounced Rashba splitting, so to say, you need to have a kind of a inverse symmetry blocking. Yeah.
Yeah, maybe. Okay, so I just want to ask you at the end, you said that you wanted to have a predictive power about materials corresponding to certain properties and so on. I mean, normally what one can do is that you can study huge number of materials, create a database, and then of course you can then try to guess.
But I'm a bit skeptical about the database because most of the time, if you have a huge database, that there is a compromise factor of not doing the calculation properly, because which is obvious, like you have thousands of different materials, then they don't really get away with the, like even if you have a heavy element in the system, you don't really consider spin orbit coupling there because it's time consuming.
Okay,
so they kind of generate more data there.
But anyway, that's that's a procedure. Of course, it's not foolproof as well as I mean, it requires huge amount of effort because you have millions of materials of different kinds.
There is some good database.
If you want to start, I mean, thinking about certain material of certain properties, of course, there are possibilities which is infinite, isn't it? You have whole periodic table available and you have combinations.
It's like a haystack.
And even if you take two element binary kind of systems, also millions of possibilities are there. So, but you said initially that if you want to find out the needle, you want to have a sensor which can choose. But you have not elaborated what is that sensor in your talk.
Okay, I did show that one. So I just wanted to show like so basically the sensor, I mean, the criteria will be like, I mean, I'm not sure if I'll have that one. So we did something on the high throughput study where we have this different criteria where we could actually see from the band structure, the effective mass, the mobility, the formation energy, the dynamical stability, all of them. And then I think it's better.
I see. So you have not essentially shown. I was wondering if you have any
Right. So basically, let's
idea like which way to start.
Right. We did something back few years back where we started with like so it was a collaboration with UC Berkeley Group and Singapore where we started with like 200 different materials. It's like a high throughput. I mean, high throughput would be much more than that. So we started with like a normal ICSD crystal structure database. We took all of the possible structure in terms of the hybrid perovskite or the inorganic perovskite, like CH3 is PBI3, like MAPBI3 kind of structure, and then the double perovskite. We started with to calculate first the formation energy. So that is the first foremost criteria. Because if you have the formation energy negative, then only you have the stability, the thermodynamical stability will be there. Then once it has stable, so naturally this 200, if you'll say, it goes down to 150 because the other are not kind of thermodynamically stable. The next thing is the dynamical stability, where you calculate the phonon dispersion, and then that positive phonon dispersion without any negative phonon dispersion presence could give you the dynamical stability. Then you try to calculate the band gap, and then you try to calculate the effective mass and the mobility, which we can actually calculate. And that's what we try to kind of correlate some of the transition spectroscopy.
But the property may not exactly relate to, for example, you want certain band gap.
Right.
I mean, same bandgap can lead to different properties. Like for example, if I want
Right,
to have
right.
interface.
Right. Yeah, for the solar cell, yeah, so for the solar cell, actually, okay, I think that
Solar
was,
cell,
so
I
basically
understand that
what we calculate is there is a kind of a property called spectroscopic limited maximum efficiency. It's a SLME. So it actually kind of was by Alex Junger. So where we could actually calculate, like, so if you have a band gap of this, as you correctly said, it may not be good for the efficiency. We could actually calculate optical absorption spectra for each of those different material, and actually from there we could actually calculate the SLME. So that is something I haven't shown. I was trying to show something else, but actually in the perovskite system, I mean, the SLME is something what can actually give you the spectroscopic limited maximum efficiency. So that is the maximum bar that one could actually talk about. So let's say if you have like all these 200 system, which boils down to like a 20 system, then you calculate the spectroscopic limited maximum efficiency there, and then you can see which are the kind of efficiency which are closely to the Shockley-Quasian limit for the solar cell efficiency, because that Shockley-Quasian limit is something where you are trying to, that is your hit on path, like the benchmark. We did that. It's just like we didn't show it here, maybe at some point, but I think we did this high throughput screening there. So those are the kind of I would say the needle problem there, where there is a magnetic property here. These are the spectroscopic limited efficiency.
Thank you. Thank you.
Yeah.
Bahadur wants
Yes.
to ask question. Yeah, so I have actually two.
Yes, please.
One you started earlier about the electron-electron interaction for some dielectric or something initially about defining some solver. Can you extend that a bit? What exactly you mean electron-electron interaction potential in the calculations?
What do you mean?
So initially when you start the talk, you said you are developing something on electron-electron interaction potential.
Okay, okay. So that is the Poisson-Boltzmann. Okay, so as
Right.
I was promised that I wouldn't say any kind of. So basically, what we do, you have the many-body Hamiltonian, and in the many-body Hamiltonian, you have the electron-neutron interaction, which is kind of basically you have the del square phi equals to minus 4 pi rho, and then if you have a solid liquid interface, like where you have a dielectric constant in the matter, it becomes as a del dot epsilon del psi equals to minus 4 pi rho. And that exactly the things. Then there is a kind of a fatter, but
the principle in presence of some material or some dielectric constant, you are
yeah.
trying to calculate electron.
Yeah, so basically we are trying to compete with already established method like polarizable continuum model like a PCM and those kind of thing, because we are confident that it will be a bit better, because in the polarizable continuum model you only have it for one particular dielectric constant. But let's say if you are given like a kind of an ensemble of dielectric constant, you don't know what are the dielectric constant of that. It's kind of a mixture of that. Then this could be actually, I mean, kind of expressed in terms of the density, the electron density. And so there is a famous Fetterbert equation is there. We're trying to kind of implement that one actually. Yeah.
Sure. Second is related to this activity. So basically, if I get the clear idea, you have a energy offset which bring from the Rashba splitting, and you have a spin texture, or in other sense, threefold spin. I mean, all the three component of spin. And also the offset between valence and conduction band.
Yes.
So any material can have the high activity. Can we generalize this or not?
No, we cannot generalize in that way, I would say. That will be dangerous to do, because I mean, there is always a trade-off into that. I mean, in one aspect, this might be really good, but in the other aspect, might be really awful. So, but if with respect to one particular perspective, one can always generalize it, but not as an overhaul. Okay, this is my go-to kind of material in a way.
Okay, so it's still,
and that's why I think we are existing, right? I mean, if you actually generalize it, then half of the problem is solved. Then there is no we don't have any materials modeling group.
But so still, it is still a material dependent.
Yes, absolutely. Yeah.
Okay.
Yeah.
Thank you, Madhav. Thank you, Sudip, for the very nice work and showing in the colloquium forum. Thank you very much to all of you for joining in. We can walk over and have a little bit of snacks in the canteen. So first, give him a big round of applause. Thank you for the AV people for keeping things on course with the Zoom.
Yeah. বলছি বলছি যখন